Okay, now that we have looked at the shared memory and the concepts there and the idea of barrier synchronization, let's take a look at some examples and let's see what is happening in um, in terms of your programming when you use shared memory and you would like to um, create calculations based off of the shared memory within a block. Let's suppose that we have a block of threads that are run, and within our kernel we create a shared memory of integer values, and let's say that we have 256 integers. I'm putting three questions here, and I want you to think about which one of these questions actually would work properly and would calculate the results, and then the results will be essentially safe. We have I'm using async threads, and then right after the sync threads, I'm reading from the index +1 and writing into its previous index. So I have two threads, and this is my memory. In the first question, each thread from index I is going to basically read from the next element over and write into its content. The next operation, I'm doing the same process, but I'm doing it for every other thread. The next operation, I'm basically averaging the value from the previous and the next thread content, and then I'm storing that content into element number I. So take a few minutes, think about it, and let me know what which one of these three, or combinations of these three elements, three program snippets, might work. So you might want to pause your video here and think about this problem, and then we'll resume in a few seconds. Alright, so I'm going to start answering these questions, and again, if you still want to think about these questions a little bit more, pause the video right here, and you can resume after you think about these problems. So if you look at the first problem, if I have multiple threads, thread number I and thread number I+1 and so forth, so each thread in one line of equation is reading from its next door neighbor element and storing inside of its location. So if you have two threads, basically three threads and so forth, each thread is looking at the next door neighbor and storing the contents into its location. I already have a sync thread here before I make the calculation, but the problem is that I'm using a read operation out of my first element, and then a write operation into, or my next element, and a write operation into my own element. And since these two read and write operations are essentially not synchronized, I may have these threads that are not necessarily synchronized with each other, and so I may be reading from the element of a thread, I mean my next door thread, but my next door thread may not have been may not have completed their data association. So this program might fail. Now to fix this problem, what you need to do is basically to create an integer temporary value, read from the values at index I+1 or index +1, then do a sync thread, and then next we will write that temporary value. And this will reinforce that we're safe to work, and then when you do that, then you sync thread again. So that this program will not work. The next program performs the same operation that I'm doing up here, but the difference is that it's only performing them on every other thread. So for example, in this case, the odd elements, so thread number 0, thread number 1, thread number 2, thread number 3, and so forth. So each odd element will convey the result of its next door neighbor. So notice that this thread works, but this thread doesn't work. And then this thread works, this thread doesn't work, or perform this operation. Therefore, the contents that I'm reading is actually safe to read and write at the same time. So this operation works. I don't have to split it and perform or inject additional sync threads there. The third operation essentially is like this first operation. Each thread is basically reading and writing, reading from its neighbors and writing into its own location. So if you look at this thread, for example, it's going to read from this location and this location, and then store the value, the average value, in its own location. The problem is that its next door neighbor also is reading its current value, its value, and its next door neighbor value, and storing it here, which basically causes the collision to happen. And so this operation also doesn't work. So the third operation here is kind of an extension of the first operation. The reason that the middle operation actually works is because I don't have any collision in using my shared memory by only performing the operations on half of the locations, not all locations. So there's no collision in the middle example here. So this example works, whereas these other examples fail to perform accurate calculation for me on the shared memory. So when it comes to programming for a CUDA platform, we realize that we have a lot of computational power with our GPU. Our GPU can perform a lot of operations at the same time, given that we make sure that we take care of all those shared memory accesses and the problems that may be caused by it, and that our problems are also essentially programmable in parallel. In order to perform better and to improve our computational performance, there are high-level strategies that we can perform, we can think of and implement that would essentially ensure that we get a lot of flexibility and a lot of incredible computational power out of our GPU. Basically, the idea is that do not waste our ALU's time, our arithmetic logic units of our graphics processing unit, to wait on memory transfers. Essentially, bring in a bunch of data that you need to work with, and not just pieces and little bits of data here and there, because when the data is being transferred, although it's fast, the speed of data transfer is not going to be comparable to the speed of operation that you get. So if you wanted to make best uses out of your GPU calculations and GPU operations, bring a bunch of data that then you'll be able to parallelize and work, as opposed to having to have your GPUs essentially wait around to get access to the data, or when the data is being transferred between your CPU or host memory and your GPU, and back and forth. Once you take care of that, you want to make sure that you increase arithmetic intensity. There are two parts, two facets about arithmetic intensity that you can increase when working with your calculations and your operations. One idea to improve arithmetic intensity is to maximize the work that is done per thread. So you don't want to have a thread that basically pulls up data, multiplies it by 2, and then stores it somewhere else. Although you can do that, that does not really utilize your computational power that you can force and use from your GPU. So what you want to do is you want to make each thread to perform as much work as possible. But then again, you want to make sure that this increasing the work per thread does not inversely impact or adversely impact the performance. The second part of increasing your arithmetic intensity is to minimize memory accesses per thread. And I'm going to talk about, going to go ahead and talk about these two aspects. So the The first aspect was easy to see how we can do, and essentially, if you want to maximize the work that each thread does, basically try to include a lot of useful operations in each thread. So for simple examples that we've been working so far, basically you're just taking an image and you're calculating its pixel values in a in grayscale, in RGB, and convert them into grayscale. So that's one easy thing to consider and to do. Each thread basically takes some values and adds them together and create a value. So that doesn't really require a lot of operations. But what if you can calculate a bunch of? So for example, if you wanted to first convert it into each picture, you want to convert it into grayscale, and then from grayscale you want to perform some additional operations. Then pack those operations all together in one thread, and you'll be able to increase your work per thread, maximize the work per thread. The second aspect we want to talk about, and we have already, is to minimize memory accesses per thread. It's best to spend very little time on read and write operations. And it's obvious because the speed of our memory is comparably, in orders of magnitude actually, slower than the speed of our processors. So what we want to do is we want to basically to take data that we want to work with from the memory units that are slower to memory units that are faster. And at the same time, there's a second aspect to that, to this increasing memory operations or minimizing access memory, is to try to coalesce our memory accesses. I'm going to talk to you about these two different aspects in a little while, but first let's take a look at the speeds that we gain with our operations. With our CUDA calculations and our CUDA hardware, we get 4 different kinds of memory that we work with. Of course, on one hand, we've seen our host memory. The host memory is basically all those pointers that we allocate and create on the CPU or on the RAM. For example, if you do int pointer something, this int pointer something is what is allocated with new keyword on host. That is a very, very slow memory. And also, another problem with host memory is that most of the time your CUDA kernels will not have access to host memory calculation. So host memory is very, very slow and we can't work on it. What we do is that we're going to go here and create another pointer for this host memory, and we put it on the device. So I'm calling this device something, and then I use CUDA malloc to allocate it, and CUDA memcopy to copy the host data that I need to work onto my memory. This goes into my global GPU memory. The global GPU memory is really good because our kernels will have access to it, and our kernels can communicate with each other within between blocks through the global memory. The problem is that global memory is fairly slow compared to other kinds of memory that we get. The next kind of memory that we've seen so far is called shared memory. Shared memory is a couple of orders of magnitudes faster and also a lot smaller than global memory. Also, another problem with shared memory, so shared memory is faster than global memory, and it's also smaller than global memory. Another problem with shared memory is that the fact that only threads in a block will be able to have access to this shared memory. So the shared memory is not accessible to threads outside of that block. Now, this aspect could be a plus or a minus if you want to think about it. So since shared memory is small, we can only use very little of this memory. Also, it is only shared within threads in a block, so that is a limitation on it. However, since this block of shared memory is shared within block threads can communicate with each other. Also, it's a faster kind of memory. So if you have a spatial operation that you need to perform on adjacent memory units, it's best to pull them up once from global memory into the shared memory, do your operations on it, And then when you're done with the result, then copy the results back into the shared memory. We've seen in a couple of examples of this so far, and the example programming that we'll do a little bit later in this unit is actually going to drive this concept home, that how you use shared memory to improve your speed. And finally, the fastest memory units that we have is local memory. Local memory is only accessible to each thread, and even threads within a block won't share this data. Let's take a look at how they look like. Local memory is fairly straightforward. We've talked about it, we've worked on it so far. I haven't really brought this to your attention because this is such a natural process for us to think about. It's completely similar to the concepts of our basic C++ programming that it was almost easy to completely ignore. If you look at a kernel, basically you've got a global keyword that tags this kernel as this function as a GPU function. Doesn't return anything, and I'm passing to it an integer, a float variable. Local variables live in local memory for each thread. Essentially, they're kind of register level memories. So, for example, if you pass a value, a parameter by value, basically passing a local float variable, that will be a local memory. Also, the memory units, the variables that you define with just normal variable definition in C++ within your kernel, they are going to be local memory. So local variables are local memory. Parameters that are passed by value, they are also local memory. So if you have one thread of operation, this thread of operation will have its own copy of in and its own copy of f as a part of it. And that the next thread will have its own copy of in and its own copy of f. The next thread is going to have its own copy of in, its own copy of f, whenever you invoke these threads. Global memory, in contrast, is essentially that part of memory that we use CUDA malloc and CUDA memcopy to allocate and to copy data to the host, from the host to the GPU or device memory. Kernels with global memory accesses are essentially just the same as the others. You've got a global tag that tags them as GPU or device. You've got the name of the function, but this time to access global memory, you pass your variables by pointer. So when you pass your variables by pointer, I'm going to call this pass by pointer. The variables that are passed by pointer will reside on global memory. So this in now is essentially accessed from the global memory. So if you look at the thread or a bunch of threads that are invoked later on, all of these threads essentially would get a pointer in that's basically points to your global memory. So all of these will have access to global memory, and the pointer in essentially points into the global memory that you can basically work with. So for example, then what you'll be able to essentially write, for example, into the thread index location. So the in is your global memory, and the index location differs from one thread to another, and so that way you'll be able to access the locations in your global memory. Remember that you need to allocate your global memory outside of your kernel in your host computation. And also you need to perform your CUDA memcopy to copy the values from host memory into this global memory. And so we already talked about these in our previous lectures. So how do we do that? Let's say that we have an array of floats, 124 float bytes, and we call this H array. We declare a float pointer, we call it D array. Then we use CUDA malloc. We pass the reference of the array, and we calculate and allocate 128, which is the same size that we needed, and multiplied by the size of float. So size of float is 4 bytes. You multiply it by 128, so that's how many bytes you get to store on the D array. So this GPU allocates the D array. So now from this point on, D array would reside on GPU. Then if you wanted to copy the data from host to the D array, it basically use CUDA memcopy, pass the D array and the H array, determine how many bytes you need, and CUDA memcopy host to device. And then you'll be able to invoke the kernel with however many threads and blocks you want over your device or your GPU global memory. Shared memory is a little funny. Shared memory kind of sort of works like global memory. It is determined with a pointer, with a location that consists of a list of bytes in memory. The difference between shared memory and local memory is that shared memory, if you create a local memory, for example, this int I, this guy is local, which means that if I have a bunch of threads, each of these threads will have its own copy of I. Okay. Now, since I define a shared float and I call it shared arrays 128, then within the block that these guys belong to, a shared memory location is going to be created, and it's called sh underscore array. And it's going to have 128 bytes in it, or rather 128 floats. So each of these guys are going to be 4 bytes. So that is going to be my shared memory. And all of these guys, all of these threads will have access to that same shared memory. The nice part about this is that if you look at the next block over, that block will have its own threads, right? Those threads will have their own copies of I as a local variable. But then they will also have a copy of 128 bytes or floats, and they also are going to call this shared array. And they'll have access to their copy of shared array. These guys will have access to their copies of shared array. And everybody in this program will have access to my array as global memory. Okay, so everybody will have access to my array as global memory, and each of these blocks will have its own copy of shared memory, and each of the threads will have their own copy of local variables. And when you call these functions, they're basically effectively the same as invoking just kernels with global memory or just kernels with local memory. So the idea is basically then, if you have local memory, each thread will have a copy of that location, that variable. If you have a variable as shared memory, then that variable or that chunk of shared memory is accessible to all of the threads within each block, and all of these memory units are called the same thing. And if you have global memory, everybody from all the blocks, every thread from every block in your kernel will have access to the global memory. Now that being said, let's take a look and see how you can order, or if you can think of what would be the speed at which these lines of code will operate. I have a kernel. Now I call this kernel something or some kernel. It's called global, so it's tagged global. It basically takes 2 pointers to global memory. Item 1, pointer to a location in global memory, and item 2, pointer to location in global memory. So these are global. Then the kernels, the threads that are running this kernel, also have 2 values, 2 variables that are shared, and then local 1 and local 2 are also variables, but they're local to each thread. So if you look at each thread, The way that they work is that each of these threads will have a local 1 and local 2. So a copy of these guys for themselves. Then all of the threads in the block will have access to sh1 and sh2. And everybody will have access to item 1 and item 2 and pointer item 2. Okay, so now that we have these, let's rank these lines of code in order of speed. The first line reads the contents of item 1 and stores it into local 1. The second line reads the local 1 and copies it into local 2. The third one reads from shared 2 and copies it into shared 1. And the fourth one reads from item 1 and makes a copy in item 2. Rank these in the descending order. The fastest will be 1, the second fastest rank 2, the third fastest rank 3, and the fourth fastest, or the slowest one, rank 4. So from numbers 1, 2, 3, and 4, basically go ahead and order these. 1 being the fastest. Alright, I'm about to go ahead and start answering this question. So if you still want to think about this question, please pause the video from this point on. And then when you're ready, continue the question. Now to answer this question, we'll have to see which one of these lines of code accesses what kind of memory. And remember the orders. Local memory reads and writes are faster than shared memory reads and writes, which are faster than global memory reads and writes. So if you look at this, the second line here, it reads from local memory and writes into local memory. This is basically a read access from a fastest memory unit and a write access into a fastest memory unit. So this is going to be number 1. The next operation is when you read from shared memory and write into shared memory. So this operation is now looking and working on the second fastest memory unit. So shared 1 equals shared 2 is gonna have the second fastest speed. The first element up here is basically reading from global memory and storing it into local memory. So this is going to be one read from a slow memory unit and one write into the fastest memory unit. So this is going to be the third operation, the third fastest operation. And the slowest operation is going to be the last, basically reading from the slowest memory unit, writing the contents into the slowest memory unit. So that would be the slowest memory operation. In fact, actually, I probably should read contents as opposed to associating addresses, and that would make it a better representation. So this is how your memory accesses and the speed of your memory accesses are ordered. Local memory is the fastest, shared memory is the second fastest, and global memory is the slowest memory on your GPU. Now, another aspect to maximizing your arithmetic intensity or maximizing your speed, optimizing your parallel process, is minimizing memory accesses per thread. Ideally, we would like to have a lot of operations within each thread, but then we want to have very little operations, memory operations, memory accesses within each thread. So we want to have our program spend less time on read-write operations and accessing memory units. Remember that all threads have access to global memory. So whenever you read and you pull out something from global memory, it will be available to all threads within your kernel. So all threads of all blocks within the kernel will have access to whatever is being read from the global memory. Now, it wouldn't be really too useful if when we read a memory location from global for thread number 0, that it would our GPU would actually just bring in just the data from thread number 0. That wouldn't really, at the hardware level, help with optimizing memory accesses. On the other hand, the process that your hardware does, the process that your GPU does, is that whenever you make an access in terms of read or write access to the global memory, your GPU goes ahead and brings in a chunk of data from global memory and caches it. This is going to be very helpful because when you need to write 1 byte or to read 1 byte from global memory, your GPU is bringing a bunch of its neighboring bytes as well. Now, if you can come up with a mechanism that coalesces the operations that threads are performing, ideally, when one thread is being performed and it accesses the memory, it brings the data for its neighbors as well. So when the neighbors need to access that data, they don't have to go all the way to the global memory to bring in data, because the data is already brought up for them as a part of the operation of their neighbor. This is called coalescing global memory accesses. When a thread accesses a global memory unit, it also brings in data from the addresses that are around it, where the data is being accessed. So if we can cooperate, if we can make our threads essentially try to work on adjacent memory units from global memory, basically that would improve our speed, because in order to perform their operation, when one of those threads make the access to the global memory, its neighbor's data are going to be coming with it. So in order to work on 3 bytes of data, I only need, for example, 1 access to the global memory. This picture is showing you what is a good coalescing and what is a bad coalescing. Now remember when I was writing, for example, a thread, and it was basically taking the number and so multiplying it by 5. So if I have an operation that does this, that thread number I basically reads its data and then multiplies it by 5 and then stores it into the location, its own location in the memory. So this is a good memory coalescing, because each thread brings in a piece of data, which means that the next door neighbor thread brings in the next door neighbor data. Next door neighbor thread brings in the next door neighbor data. So if this thread needs global access and makes the global access, it's going to bring with itself the data for the next door neighbor threads. So as a part of one memory access, 3 threads, for example, in this hypothetical example, will have the data to work with. So basically this compacts in essentially a bunch of data for neighboring threads to work. Bad coalescing is when you have strided axes. So for example, if my threads are basically doing something like this, thread of every I, for example, if I %5, then do the calculation, right? So for example, this thread needs to work on this data, and this thread needs to work on this data, and this thread needs to work on this data. So if my data is strided enough in that each thread memory access is far away from their neighbor thread's memory accesses, basically I would have to go for every single one of these threads to make a global memory access, and that would slow down my CPU, my GPU. So GPU is most efficient when your thread's memory accesses are coalesced. So a good example of coalescing of the memory and memory operations, memory patterns that we talked about, was the idea of transpose. So if your data, for example, is in row major and your operation needs to be in global column major from your global memory, that would make up for a very bad strided memory access. So if you just perform a simple transpose operation, you reformat your memory accesses to row order memory accesses, which is what your data may be originally in, and therefore you will be able to improve your performance. So Good coalescing is when you have threads accessing their data, the neighboring threads accessing neighboring data. Band coalescing or striated access is when threads are accessing sporadically or rather sparsely in the memory. I have another quiz here for you to think about, and the question is which one of these memory accesses are good coalesce memory accesses. So I have another kernel, I'm calling it some kernel, and it's basically accessing the pointer item in global memory. So if you have a global memory and we're calling this global memory item, and this is my item pointer, and I have a local memory value called value, and I calculate memory a local variable index that's going to be my thread index. I'm writing, so the first line writes value into the location item. The second line writes value into every two items. The next line reads item into value. The next line reads the block width over 2 plus index. So essentially it reads next half of the block. The third operation does item at index equals value times item plus block with plus index. So essentially it brings in a whole bunch, from half the side of the block in, it brings in the data to copy into the beginning of the block. Then the item block width minus 2 minus index equals value. And the last operation basically multiplies the item at 5 locations or 5 times the location into my current location. So think about these questions and basically with like either a yes or no, tell me which of these memory accesses are good coalesce memory accesses and which of them are not coalesce memory accesses. Okay, if you still need to think about this problem a little bit longer, please feel free to stop and pause this video, and then you can resume after you're ready to listen to the answer. The answer basically is essentially very easy. So here's my item, the input memory, and then I have a bunch of threads. Now let's look at the first item. The first item basically stores the value in the location of index for each thread. So if I have a value, a local variable, remember that each thread will have a local variable called value. It's going to basically take its own local variable and then copy it into the thread location. So this is a good example of a striated memory. This is a good example of a coalesced memory pattern. Basically, each thread is writing into its own location, and since the threads are essentially writing their own numbers, the numbers are coalesced. So this is a coalesced memory access. The second line basically stores its value into its thread location times 2. So what happens here? This were my threads. So the first thread basically takes the value and writes it into I. The next thread takes the value and writes it into I times 2, I times 4, I times, or rather 2 times I for each thread. So this is basically a striated memory access, and we talked about it because when I'm writing into this memory location, essentially my GPU is only basically writing into every other thread, so I would have to have more memory accesses per write operation. So this is a striated memory access. The next line, it reads the memory unit and stores it into the value local item. So this is basically the same example that we talked about, the reverse order of operation from the first example. So you get your memory units are going to be stored in a coalesced pattern into the local memory. So this is good, coalesced memory. The next operation is actually kind of a little interesting, and the way that it works is that now for this operation, each thread will look at an offsetted index. So it looks at its own index and goes and pulls up the data from half the size of the elements in, and then stores it into its local variable. So basically, for example, if this was the half of the global data, it's going to bring in that data into this thread, that data into this thread, that data into the next thread, and that data into the next thread. See, although I left the first half of the block or the global memory, I still have a coalesced memory access. So the third value, the third line of code is also a coalesced memory pattern. The next line basically is the same as the above. It just multiplies it by some value and then stores it into the index location. So if you look at this, this is also another interesting example. The way that this works now is, let's suppose that again here, this is my half of the data. So I'm going to pull the data here into this thread, multiply it by the global value, and then store it into the thread location. I'm going to do the same. I'm going to bring this data from the next door neighbor, multiply it by my local variable, store it somewhere. Next, bring it in, multiply it, store it. Bring it in, multiply it, store it. So my read memory accesses are coalesced and my write memory accesses are coalesced. So this is also a good example of a coalesced memory access. And this is a good memory access there. The final or the next operation, also basically this operation is the same as this operation up here. It's basically the write. You basically read the value of your current index and then you store it into memory location. So basically the idea is that here I'm going to write this content here, write this content there, write this content there, and write this content there. See, now I still have memory coalesced memory access. Although I'm now going backwards into my global memory, that doesn't matter. That going forward or backward in memory doesn't really make any difference in terms of your coalescing memory. In fact, you don't even know where you're going forward or backward because these are happening at the same time in parallel. So all the chunk of coalesced memory accesses are going to be applied in parallel. So you've got a coalesced memory access there as well. And finally, when you have a value that you're reading from index times 5 and then storing into the index, that is going to be a strided memory access. And to show you how it works, basically the last line I'm reading, for example, for I times 5. So for example, for I equals 0, this is reading the content, multiplying it and storing it. For I times 1, it reads here and then, or rather reads from I times 5, multiplies and writes, then reads from I times 5 and multiplies and writes, and reads from I times 5 and multiplies and writes. So this read pattern is going to be a strided read, which is not a good idea. So this last operation is as a strided memory access. So the last operation and the second operation are strided, and then you can easily see why they are strided. See, when you have access to multiples of your thread index and work with index or a local variable, you would effectively get a strided memory access in that sense. Now, let's take a look at another problem. And it's actually kind of a relevant problem, but it's basically a different issue when we work with parallel programs, and it's called thread collision. When you have shared memory accesses and threads read and write from the same memory unit, that could be either the shared memory of the block or the global memory that all threads from all blocks have access to and share, there's a potential problem. And that is what happens when two or more threads will try to access the same memory unit. Only one of those threads will be able to access the memory unit and perform operations. And all the other threads that are colliding with this thread either won't be able to perform their operation, they just move on and not perform the operation at all, or they have to be serialized. Obviously, thread collision is a bad issue, is a problem, is bad. If you can solve this thread collision, you might end up in a situation in which effectively you're slowing down your process for allowing all threads to be able to access the memory units that they need to access. Or worse, if you won't be able to resolve these collisions, you won't be able to even detect them. And so threads will basically attempt to write. If the memory was blocked and they couldn't write, they just move on, and the data that you have been working with will be lost forever. So to show you a very good example of this, I'm going to show you in pseudocode, and then maybe later on I'm going to just write this program for you and show you how it actually looks like and how it works. So if you have a global kernel that you define, so I have some kernel here, and it basically is defined as a global kernel, so it's basically a GPU item. It takes a pointer to the global memory with a size, and then what I'm attempting to do here is to basically increment each index of my global memory by once, and essentially try to calculate how many of my threads belong to each item of my global memory. So the problem is actually a fairly simple problem. I have a global memory that, let's say that it's only 10 bytes long. Okay, so it starts from byte number 0, byte number 1, 2, 3, 4, 5, 6, 7. So let's say that we have 8 bytes, 8 memory units, 8 integers. And this is called my item. It's a pointer to this global memory. Then I'm going to invoke a bunch of threads, and we'll have each thread to calculate the modulus of its own index and write into that memory location. Basically add to the content of that memory location. So let's say that I'm writing, let's say that, I don't know, like 200 threads, right? So I have a bunch of threads, and each of these threads will have a thread index, right? Then what I'm going to do is that I'm going to assign each of these thread index and have them calculate the modulus of their own index number by the size of my thread. So the thread number 0 is going to have I equals 0. Thread number 1, 2, 3, 4, 5, 6, 7, 8. Thread number 8, its modulus is going to be 0. 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, so on and so forth. So thread number 0, thread number 8, and thread number 16, they all will have modulus 0. So what they're going to do is that I'm asking these threads to each to go in the element number 0, and each of them to add 1 to element number 0. So basically, item number 0 at sub 0 would be 3, because 3 threads are supposed to write into that unit. Item number 1 after the operation of my kernel should be 3, because thread number 1, thread number 9, and thread number 17 all will attempt to write to item number 1. So if I write this program and I run it with a bunch of threads, I will not get a really nice result. Here's a run of the example that I performed. I ran that program. I made the array size 5, so essentially I had the item basically have 5 elements in it. So element number 0, 1, 2, 3, 4. And then I ran 50,000 or 5,000 threads, right? So in 5,000 threads. So thread number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to 5,000. So thread number 0 wanted to add, thread number 5 wanted to add to element 0, thread number 5,000 needed to add to element. Thread number 1 and 6 and 11 and so forth, they all attempted to access the element number 1. When I ran this program, each location should have 1,000 threads written inside of it. So each location should have number 1,000 in it. I ran it a bunch of times. Ran number 1, gave me different numbers, 294, 291, 293, 295, and 295. I ran it again. Run number 2, I got 291, 293, 293, 294, and 293. Run number 3, again, totally different number, a totally different result. What happened? What was the problem? Here is the problem that happened. So I have 5 elements. Item number 0, 1, 2, 3, and 4. Now, in my program, what I have here, each thread will calculate its location and attempt to read the content of that location, add 1 to it, and store it back into that location. So thread number 0 will attempt to read whatever item had at location 0, add +1 to it, and then store it back. Thread number 5 is attempting to do that same process. Read whatever is inside of item 0, add +1 to it, and then store it back into location 0. Now let's see what happens here. So thread number 0 and thread number 5 want to perform this operation on item number 0. Okay. Ideally, if thread number 0 comes in and reads the value, it's going to read 0, and then it adds 1 to it, then it's going to be 1. Then it stores 1 into item number 0. Then ideally, after that happened, thread 1 comes in, reads 1, adds 1 to it, which becomes 2, and then now stores 2 into item number 0. So ideally, in the case that both threads had a serialized access to this memory, I would have number 2. Let me just rewrite this for you in a different way so you'll see what are the options. So the first option, the first possible thing that might happen, and this is my item 0, right? So let's say that item 0 started at 0. Now, if thread 1 comes in, thread number 0 comes in, reads 0, adds 1 to it, then it becomes 1. And if right after that happens, thread number 5 comes in, it would read 1, adds 1 to it, and then stores 2. So the first element reads 0, writes 1. The second thread reads 1, writes 2. Okay, so that's one potential possibility. However, this is not the only possibility of shared memory access in this case. Another possibility is the possibility that thread 5 comes first. So item is 0, and what if thread 5 comes first? It reads 0, it adds 1 to it, and stores 1 into the memory. So now 0 becomes 1. Now if after that write happens, thread number 0 comes in, then thread number 0 is going to read 1, add 1 to it, and store 2 into the memory. And that would be good. 2 threads have access and incremented the element twice. There are 2 other possibilities that are at play. What happens if thread number 0 comes in? So my element item is number 0. Thread number 0 comes in and makes a read access. So 0 pulls the read or reads 0 from my element. And while it's adding 1 to it, what happens if thread number 5 comes in? If thread number 5 comes in and attempts to read from the memory. Since thread number 0 has not finished its write, my thread number 0 is going to also, my thread number 5 is going to also read 0 and then adds 1 to the 0. Now while thread number 5 is doing that, my thread number 0 has gone in and written 1 into the element. The problem is that my thread number 5 has already read 0, adds 1 to it, and then tries to write 1, which is the increment of whatever it had written, into the location item number 0. The problem is this case. When two threads read from the memory unit, but the first thread has not finished updating the memory unit before the second thread makes the read, it would cause the problem. And as you see, what has happened here is that at least 1/5 of the threads got to actually increment the actual value of my element. So instead of 1000, I get about 300. Actually 1/3 of the element, which makes me believe that 2/3 of my threads in this case actually written the same number, and didn't really get to implement the updated element in my array. So this is another potential problem when you're working with shared memory units like shared memory or global memory. You won't be able to, you have to be very, very careful about memory accesses, because you may end up with the problem of a collision or colliding in memory. Now to solve that problem, there's a workaround. We can basically serialize our thread accesses. And to serialize our thread accesses, we will use atomic operations. Now, if you look at my previous problem, what I did is that when I calculated the location of each thread in the element, I read essentially from my element, then I incremented that value, then I wrote that increment result into my element. Now, if I had multiple elements accessing, then they may have had parallelized read accesses to this unit, and that may cause the problem that we saw here. To serialize those memory accesses, we basically perform atomic adds. Atomic adds essentially make sure that when a memory unit accesses a location, when a thread accesses a location, it locks that location for any other memory and any other thread to access. This solved my problem. Remember, the problem that was caused was like this. I had a memory unit, and then I had two threads that attempted a kind of parallelized access to this memory. Let's call this read, and then operation, and then write. Okay, read, operation, and write. So the problem that was caused before is that the first thread came in, it performed the read operation. While it was working, the second thread came in, and so now the second thread performed its read operation. Then it did the first thread did operation and finished up and wrote the results in, and then the second thread performed the operation and then wrote its result in, thereby invalidating the first thread's result. That was the problem that was caused with just a basic collision with my threads. To solve this problem, what I can do is I actually can basically prevent this second thread from accessing my memory while the first thread is working on the memory. So let's suppose that this thread comes in and it makes a request for read into the memory unit. That's fine. When it does that, with the atomic operation, it's basically going to put a lock on the memory unit. So if another thread comes in and wants to access by read into the memory unit, it will be not given access. So my thread at this time would have to wait until the first thread performs the operation and makes the write. When it does make the write, then it's going to basically open up the lock, therefore allowing other threads access to the memory. So now my second thread was waiting. At that point, the wait will be over, and then the second thread will lock the memory and read the contents. and then perform the operations and write the result. When it does that, then it's going to basically again open up the lock for another thread to perform the calculation. This kind of locking of the memory and performing operation is done through atomic operations. So what you will do is that you perform, instead of doing item I equal something, you basically do an atomic add, pass the pointer to that location, and perform the value that you want to add. When you do this, then when multiple threads need to access and perform this operation on, the first thread that accesses, it's going to lock it, perform the operation, do the add, and release the log for others to calculate. There are certain limitations to performing atomic operations. Probably the first limitation is that there are only certain operations that are supported. The operations that are supported are add, subtract, and multiply, and things of that nature. There are only certain data types that are supported by add operation, and that includes integer, character, floats, and so forth. So if you have a certain abstract data type or a data type that you have created yourselves, you won't be able to use atomic operations on them. Also, there are certain compute units that support atomic operations. I believe compute unit 2.0 and over support atomic operations, which means that if your graphics card is an older graphics card that only supports compute 1.5 or anything less than 2, you won't be able to perform atomic operations. And finally, practical problem with atomic operations is that they are slower. And as you can see here, they're basically slower because of the additional overload in the operation that they have, as opposed to just a simple add. And also, the other reason that they're slow is that they essentially serialize memory accesses. And we saw this by the comparison of when we had multiple threads accessing the same memory unit. Since when the first thread gets in, locks the memory unit, the second unit would have to wait, which essentially effectively makes this parallel access effectively a serialized access. So this guy needs to go, and when it's done, the next guy needs to go. That serialized of access is the problem that it's actually the solution of a specific problem, but it's essentially a problem in itself. So if you get into a situation in which that you have a lot of threads, and effectively by doing atomics you serialize them, then that is the point that you might want to rethink your problem in terms of reformatting it into another problem, another formulation that allows for more parallel accesses as opposed to what you have here. Now, the simple workaround in terms of using only certain operations is to utilize atomic CSA. Basically, it's a compare and swap operation. So, for example, if you had a complex calculation, for example, I don't know, like calculating the power of something, you will be able to custom write with atomic CSAs your operation. Finally, before we go to our lab examples, I'm going to talk about another problem in terms of parallel programming that you want to be aware of, and that you want to be able to first be able to analyze that problem and also try to avoid this problem. It's called thread divergence. Most of the programs that we've written so far have not had or may not suffer from thread divergence because the problems that we've written so far, we have not had any conditionals in them. Thread divergence is caused when you have in a parallel program some threads that might take longer than others to perform a certain kind of calculation. When you increase the computational complexity of your threads, or rather, if you remember, we said increase arithmetic intensity of the threads, inevitably you bring in more programming logic into the thread, more programming logic into the kernels, which essentially may make some threads need to work more than other threads. And when that happens, it basically causes your threads to take different routes of operation, and the byproduct of that, they would diverge in their calculation of certain or performing certain operations. So they would take different times to compute. And when you have a lot of different threads and different blocks that they have a lot of different conditions that they need to perform, that would potentially cause your threads to converge. So for example, if your block goes like something like this, you have a kernel, and the kernel is basically underscore global, and then stuff, and then here you'd basically calculate if something happens, then do this, else do this, if something, and then else if, and some for loops and so forth. That all these conditions are essentially tied to the location of your thread, or the number of your thread, or its location in the block, that may make threads to take different routes. So for example, the first thread might take this route and then exit. The next thread might take this route and then this route and then exit. The next thread might just take this first else and then go to the last else and perform different kinds of things. So if your thread's going through different routes of calculation, different flow of operation, you might end up with threads that are kind of diverging and causing problems. Now, this thread divergence basically is exacerbated, made a little bit more severe when a part of these conditions that your threads are taking, or part of these routes that these threads are taking, is caused by loops in your operation. So this is a very good example of what happens. For example, if you have a bunch of threads that come in, and those threads and the block needs to perform a loop operation. So a pre-loop operation is going to be performed. Then as a part of that pre-loop, some threads may just skip the entire loop and go and finish the post-loop operation. Some threads may take a few of the loop steps and then move on. And some threads may actually have to run the entire loop to completion to perform. And then all threads will effectively perform some post-loop operations. Now, the problem is that since we invoke the kernel, and remember, we invoke a kernel by performing the kernel name and the size of the grid and the size of the block and the parameters that are going past to it. As a part of that, we're going to invoke a bunch of blocks, and within these bunch of blocks, we're going to have a bunch of threads. Right? So, if we have a loop that passes these threads into a different route of operation, since the next kernel will have to wait until this kernel's execution is completed. And in fact, since each block of threads would have to finish with each other, so, or all the threads within the block would have to finish to relieve or release the block of your streaming multiprocessor. Effectively, even if a few of your threads have to complete the entire loop to completion, none of the threads will be released. Thereby, the streaming multiprocessor would be effectively bogged down for operation, even though a lot of threads have calculated and finished their operation as a result of thread divergence. So this is the section of your computational power that is going to be lost. So your streaming multiprocessor effectively requires this much process plus the pre-loop plus the post-loop. But while this process is being performed, even the empty released idle part of streaming multiprocessor that other threads were working on, it has to basically effectively sit idle until everybody's work is finished. And this is a particularly bad situation. So the idea is when you end up with a thread computation that requires a lot of computation and a lot of conditionals and loops, try to balance out your operations in that all of the threads will roughly take the same amount of time. Now, we're probably not going to get into this, the details of this calculation and how we write programs to perform better and avoid thread divergence in this semester, but there are really nice tools, essentially with CUDA, debugging mechanisms, and the Nsight debugger that NVIDIA has, that you could essentially optimize. It shows you the occupancy rate of your GPU, basically telling you what part of your GPU streaming multiprocessors are idling, and if you invoke a kernel for completion, what is the percentages of idling threads, and when you have occupancy of less than 60–70%, you might want to rethink your problem to try to get your occupancy rate higher. And if we get to it, I'll probably touch up on the efficient programming a little bit later, probably the last week of the semester or so, to tell you about different potential problems and potential solutions. But these are essentially the high-level issues that we might get into: thread divergence, thread collision, and serialized versus parallel memory access pattern, or rather strided or coalesced memory access patterns that we should essentially think about and be aware of when we're programming. Now, to summarize your problem, or rather this unit, we talked about GPU hardware. We looked at streaming multiprocessors, special processing units in your GPU, and blocks and threads. We talked about different kinds of memory models, global, shared, and atomic operations within your shared memory accesses. We talked about synchronizing your memory accesses and trying to avoid problems when threads collide, and to try to solve the problems of wrong calculation because of thread collision. We also talked about GPU programming efficiently, essentially. Try to access our memory faster by performing coalesced memory patterns, memory accesses, if you need to go to global memory, and to perform faster memory operations inside of your shared memory within a block when your threads can communicate with each other within a block through the shared memory. And finally, we talked about avoiding thread divergence and trying to write programs in such a way that you would have very few or very little memory collisions, and or rather very little possibility for threads to take drastically different routes of operation, and therefore decreasing your GPU and streaming multiprocessors occupancy. Now, with that being said, I'm going to just go over very basically here, tell you about your programming assignment, your next programming assignment. You'll have 3 weeks to perform this programming assignment, and there will be a PDF file explaining what you are supposed to be doing with this programming assignment. And the idea is that you have worked with an image threshold. You started with a grayscale image and you turn it into a black and white image, and that was a map operation. Then we looked at another interesting operation in taking your GPU, your image on the GPU, and using a gather operation to convert an image from RGB to black and white. So that was a gather operation that you performed. This week, for this unit, you're going to perform an interesting application. You're going to perform a gather operation. But to speed up this operation, you're going to use shared memory. How are you going to do that, and what is the example of it? We want to do an image blurring example. In an image blurring or image filtering, what you will have is you will have an original image. So the image is going to have a bunch of pixels, a bunch of rows, and a bunch of columns, right? And so the idea that programs such as Photoshop, will perform is to blur an image, is to perform a nearest neighbor averaging of your image. So you look at your original image, and what you want to do is you want to calculate, and I call it f, a function that converts and changes the value of each pixel by looking at its neighbors and replacing the value of the pixel with the average of all the neighbors in that image. So the idea is, for example, if I wanted to look at and calculate this image location right here, what I will do is I'm going to go here, and this image location was the third in and the second row, so this was my image. So what I'm going to do is I'm going to look at a neighbor here of that pixel, and then I'm going to sum up all of its neighbors' values and divide them by 9, and then store the average into the pixel location. So this is going to be essentially the average of I minus 1, j minus 1 to I plus 1, j plus 1. That's the location. So you get the number here plus 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 here. You add these up, and then you divide it by 9, and then you store it here. Now, what about the next door neighbor? For this guy, I'm going to basically go in and then do the same thing for its neighbors. So you're going to take this guy, this guy, this guy, and you sum them up, and then you store them in. Now, you can do this just with a simple gather operation and bring in your results into the final image. It is going to be very slow because for each pixel, you're going to have to perform a local operation to the global memory. And that global memory access is going to slow you down. An alternative to do this is that you would basically take your original image and then break it into blocks. And let's say I'm going to do this with 4 blocks. Okay. So the idea then in this case is going to be that you're going to take this image and break it into 4 blocks. So let's say that I'm going to break this image into these 4 blocks. Okay. Then what you will do is that for each block, you basically pull up this data and copy it into a shared memory. So effectively, you're going to have 4 shared memory units that will have the data. Then what you're going to do is that you're going to be performing your calculation of the pixel averaging instead of doing it from your global memory, just like you did with the color conversion. You will perform your averaging in the shared memory as opposed to the global memory, making it much faster. And then you store the results from the shared memory unit, basically, to each of the corresponding blocks, right? So go ahead and study your your examples here, and basically the PDF file that is posted, and try to work on this project. It is going to be a little bit more complicated than what we have done so far, and I highly recommend you start working on it and strategizing and thinking about it. So the steps are 3 steps. You break your kernel into multiple blocks. For each block, you create a shared memory location. Pull the data from the global memory into the shared memory location, perform your calculation, and then store the result inside of the output. And hopefully, this will be a really nice program for you to get some experiment and experience with this program. Now next, what I'm going to do is I'm going to show you a very nice example of using shared memory, and hopefully this will help you a little bit with your programming project here. And in this case, we're going to calculate a two-dimensional image, create a two-dimensional image based off of a two-dimensional equation. To perform our equation, we perform the operations onto the shared memory, and we store the results into the global memory for the final display. And this should show you what happens if you don't use shared memory and synchronization, and when you do that, what happens in terms of how, or essentially how you can utilize the shared memory. So with this, I hope that you enjoyed the lecture portion of this class, and you're going to start the next unit, or the next part of this unit is going to be the lab section that shows you programming shared memory operations and block processing.